Video, we have a liquid that's flowing through a horizontal pipe of radius 0.02 meters, and it's just the pipe bent straight upward through a height of 10 meter, and it joins another horizontal pipe of 0.4 meters. And it wants us to find the volume flow rate that will keep the pressures in the two horizontal pipes the same. So here's a diagram to help you visualize. Here's water going through the horizontal pipe at the bottom there. So you notice here it's going to go up this vertical pipe, which is given as H, and H here is 10 meters, and then it's going to go through a wider pipe here that's 10 meters above the initial level. Okay, so I do want to point out here V1 is drawn slightly longer because in a narrow pipe the velocity is faster, and here in a more wider cross section area, the velocity here or the speed here is going to slow down. Okay. All right, so let's go ahead and find this volume flow rate. So to go ahead and start, I would like to remind you for this particular problem, I'm going to go ahead and use this particular continuity equation. A1V1 is equal to A2V2, where A is the area, V here is for the speed at each of these points. So 1 being at the bottom, 2 being at the very top. All right, so this is your flow rate function. I'm not going to use V over T because based on the information that's given. So I do want to remind you that A times V is flow rate. At this point, you can do flow rate is equal to A1 times V1, or you can do A2 times V2. It is entirely up to you. So pick a side. You either go with left or right. So if you go with left side, then you need A1 and V1. If you pick the right side, then you need A2 and V2. I'll just pick the left side. Okay, they're both equal to each other, so it doesn't really matter which side you choose to do. All right, so let's go ahead and do this. In order to find the flow rate, I need A1 and V1 based on the information given. I can go ahead and identify this as R1. So the radius of the narrow pipe at the very bottom is given as 0.02 meters, and then the radius of the wider pipe at the very top, at the diagram here, that's 10 meters above, that is 0.04 meters. So as you can see here, we're given the radius, which means you know the area. So you know A1, you know A2. What you don't know is so V1 and V2, okay? Because area is simply pi r squared, and pi is a constant. So really, they didn't give you A1 directly, but they did give the radius, so you know what A1 is, and likewise, you know what A2 is, because the two radii are given, okay? So in order to find the flow rate, I need A1 and V1. So again, I'm just going to go ahead and choose the left side, A1 and V1. So I need A1, I need to find A1 and V1. So to do this, I'm just going to go ahead and set up Bernoulli's function. The key phrasing here in this particular problem, it says what flow rate will keep the pressures in the two horizontal pipes the same. Because it wants to keep the pressure the same, I can go ahead and cross out P1 and P2. Well, why P1 and P2 does exist in Bernoulli's function here, both of them are the same. So therefore, I'm just going to go ahead and cross it out. At the same time, I'm going to go ahead and cross out this rho GH1. H1, I'm just going to take the ground as my 0. So therefore, the starting height is 0. So hence, rho GH1, it would just be 0 because H1 is 0. Okay. So I'm just going to simplify that down to this statement here. 1/2 rho V1 square equals 1/2 rho V2 square plus rho GH2. But as you can see here, rho, or the density of the water, whatever liquid this is, it has to have the same density throughout the movement. So here's rho, here's rho, here's rho. Rho appears in every term. So I'm going to go ahead and cancel that out as well. So from here, I'm just going to go ahead and just kind of do a little math here. I'm just going to simplify and clean this up a little bit so everything is carried down except for the rho. But as you can see here, this is 1/2 V1 squared equals 1/2 V2 squared, and then this GH2. I'm just going to go ahead and multiply both sides by 2, just get rid of this fraction. Okay, so you know how there's 1/2 here, and there's 1/2 here. If you multiply by 2, 2 will cancel out the 1/2, which will make it 1. 2 times 1/2, what that'll make that 1, and then 2 times GH2, that'll make it 2 GH2. So here comes the work. All right, so here I'm just gonna go ahead and get rid of the fraction. It's up to you, you don't have to, but really, or you can just multiply both sides by 1/2 or 2/1 here. All right, so to do that, I'm just gonna go ahead and simplify my work down to V1 squared equals V2 squared plus 2 GH2. Once again, that 2 comes from multiplying both sides by 2, just to clean up a little bit. All right. Here, I'm just going to do a little plug and chug. G is 9.8, and then H here is just 10. We're dealing with conservation energy here, so I'm just going to go ahead and plug in G as 9.8, not negative. As you can see in this particular statement that I have previously, V2 is unknown, right? In order to find flow rate, once again, I need A1, which I do know because the radii of the first horizontal part of the pipe is given as 0.02. What I don't know is how fast the speed is flowing through this, section of the pipe. So, in order to find V1 square, I need to figure out what V2 is, and then 2 times 9.8 times 10 is just 196. I just carry the units down here for you. If you want, you can just leave the units out. It seems like everything's already in meters, so things will cancel nicely for you here in this particular problem, okay? All right, well, to find V2, I need to set up my continuity equation, right? Well, I know A1 V1 is equal to A2 V2. So here, I'm just going to go ahead and isolate for V2 because that's what I need. I'm going to keep V1. So in order to keep V1, I need to get rid of V2. So in the continuity equation, I'm going to go ahead and solve for V2 simply by dividing both sides by A2, okay? Well, once again, A1, you kind of know because it's just pi r1 square. A2, you know, is pi r2 square. And then V1 here is my unknown as well. So I'm just going to go ahead and square both sides. Now, why am I going to square both sides? That's because over here in my work in black here, I need V2 square. All right, I don't need just V2, I need V2 square. So I think the easiest way is to just square both sides. So A1 square is just A1 square, V1 square is just V1 square, and then likewise on the bottom. And now I have a statement for V2 square, right? So this is just a little visual trick. You don't need V2, you need V2 square. So why not just square everything so that you already have that term? So I'm going to go ahead and substitute out A1. A1 is pi r1 square, but that term is being square itself, right? Because the area is being square itself. So make sure you use parentheses here to, make sure you distribute the exponent properly. V1 squared just gets carried down. Likewise on the bottom here, A2 square. But the generic function for area is pi r square. So pi is right there, r is r2, and that's square. But then a itself is being square, so make sure you include that exponent 2 there. So if you clean up a little bit, the pi square term will cancel out. And then r1 square is going to be r1 to the 4th power, because this is power. And then v1 square I just carry down. And then likewise, like I said earlier, pi being square on top and by pi being square on the bottom will naturally cancel out. On the bottom, the only term you have left is r2 to the 4th power. Okay. So from here, we know what r1 is. We know what r2 is. r1 is 0.02, as identified earlier. r2 on the bottom is 0.04, and then v1 square is what we don't know. So therefore, I can just simplify this and then substitute it in. Okay, so instead of v2 square, I can substitute all this wonderful stuff in. r1 to the 4th power times v1 square divided by r2 to the 4th power. And if you simplify this on your calculator, so if you want, take a minute, pause. r1 is 0.02, so if you type in 0.02 to the 4th power divided by parentheses 0.0625 to the 4th power, you'll get a coefficient of 0.0625, and that will be in front of v1 square because v1 square is unknown. Okay. Other than that, as you can see, we have a v1 square on the left side, we have a v1 square on the right side, so combine like terms. So to get v1 square on just one side, I'm going to subtract this 0.0625 from both sides. So over here, the coefficient is just a 1. 1 minus 0.0625 is 0.9375. The v squared term is carried down, and that all equals to 196. So I'm running out of space here, so I'm just going to go ahead and tell you, to get v by itself, the first step you need to do is divide both sides by 0.9375, and then square root that answer. And if you do that correctly on your calculator, you'll get a value of about 14.46 meters per second. Okay. Well, I just found out what this speed is going through this narrow section of the pipe at the very bottom here. So V1 here is 14.46, and I know that as it goes up and it goes through this wider section, cross-section area, it's going to slow down. Okay, but I need to find flow rate. Well, to find flow rate, I need A1 V1. Once again, I just chose the left side of this function. If you wanted to, you can use A2 V2. Then you would just have to do the same step except for solve for V2. Okay. Well, flow rate, once again, is Q. Q is flow rate. That equals to A1 V1. Well, A1 is pi R1 square. V1 is just V1. I already found that previously in my work. So I'm just going to go ahead and plug and chug. Here's pi, gets carried down. R1 is 0.02. I want to square that. V1 I just found to be 14.46 meters per second. I left the units out here because I'm running out of screen. I'm running out of space on the screen here. And then if you simplify this in your calculator, you get that the flow rate is 0.018 meters cubed per second. Okay. All right. Other than that, that is the answer for this particular problem. I hope that helps. Stay nerdy. Don't be whack.